Hi, and welcome to the first video in a series on enumerative combinatorics. In this video, I would like to give an overview of what enumerative combinatorics is, some of the methods that are employed in this field of math, and a few basic results. So enumerative combinatorics, as one might be able to tell from the name, deals with enumerating certain structures, analyzing them and finding certain patterns and results from them using the techniques of combinatorics, which can be informally thought of as how to count. It deals very heavily with permutations and combinations, for those who are familiar, ways to choose certain things, certain sequences, and there are many different ways that one can approach a type of enumerative problem, so to speak. There are some ways which involve a lot of algebraic or symbolic manipulation, and some of those are really inevitable with certain kinds of problems, as we will see. A very useful kind of algebraic manipulation is that of the generating function, as we will see. A generating function is a algebraic representation which can be manipulated in a certain way, which really helps combinatorial problems. And there's also sometimes asymptotic approximations for behaviors of functions that we don't necessarily have closed forms for, which provide good estimates, and asymptotic expressions are frequently used in, for example, analytic number theory. And very useful type of solution to an enumerative problem is a combinatorial interpretation. And this is sort of a less precise sort of solution to define than, for example, a sequential linear way of going about an algebraic manipulation. It more has to do with finding the connections for the reason why a certain structure is enumerated the way it is. And oftentimes the way that these combinatorial proofs go is that if you want to show that two sides of an equation, let's say, two quantities are equal, you define something, or you call upon something, a third auxiliary structure, and you show that they're individually equal, those two sides of the equation, to that third thing that you just defined. So oftentimes that'll be the method, very vaguely speaking. And a lot of combinatorics also deals with, as we will see here, like the idea of a set and that of a multi-set. You might have heard of a set, you might not have heard of a multi-set, but they're fairly straightforward, and they're the first few results in the series about enumerative combinatorics. So let's start by setting S to be this set over here, where x1 through xn are just indeterminates, let's say, or variables, where the cardinality of S, which we will denote by a hashtag, sometimes there's a notation like absolute value brackets, but just the hashtag is unambiguous. We'll call this an n set, which is short for n element set. So if S is an n set, a frequently appearing problem is, well, how many subsets of a certain kind are there of a set? And of course, the first step to that kind of problem is how many subsets are there for any given set, just in general. And the answer to that, which we will find, a simple way to go about it is going term by term. If we think about S as almost a sequence up to permutation of the elements, we can go one by one. We can go through x1, x2, through xn, and if we have a subset, which we don't know much about yet, we can go recursively and say, well, if I have this element x1 in S, either x1 is in that subset or it is not. So these two are mutually exclusive events. You can't have something that's both in and not in a set. And so you're going to have two options for x1, two for x2, so on and so forth, for however many elements you have. So if you have n, the cardinality of S, then the number of subsets that you can define is 2 to the n. And we're going to define, this is not like standard notation. In fact, what you'll see is rather something like P of S, which denotes the power set of S, some terminology from set theory, which is the set of all subsets of S. And now this terminology makes sense because we know that, in a sense, it's like it's like taking 2 to the S, because there's so many subsets that you can form with n elements. And we define this auxiliary set, which is denoted 0, 1 to the n. And this consists of all sequences of, let's say, of all tuples, E1 through En, let me just add a comma here, such that for each EI where I goes from 1 to n, either it's equal to 0 or it's equal to 1. You can think of this as all binary strings that one can define. And for this, of course, since you have two choices for each one, we have that this cardinality is going to be equal to 2 to the n. And this is really a more explicit way of writing out what we had talked about earlier, where you can just go element by element and say, is this in the subset or not? It's a more formal way of writing it. We can define the map, which we'll call by theta, from 2 to the s, the set of all subsets of s, to this 0, 1 to the n, where n is the cardinality of s. We define it by theta of t, t being a subset of s, and it maps into this tuple E1 through En as follows. We have E sub I is equal to 1 if the element xi is in T, where xi is the ith element here in S, or ei is equal to 0 if it's not in the subset. Really, this is an equivalent definition. And sometimes theta of T is referred to as the characteristic vector of T. This is not extremely important terminology, but I'll include it regardless. And we can look at an explicit example now. So letting n equal 5, where we want to look at 0, 1 to the 5, the set of all binary strings of 5 elements, we can define the subset T of x1 through x5, x1, x2, x3, x4, x5, such that T is equal to x2, x4, and x5. We're just choosing these three. So we have theta of T now, where we can think of it as they have to agree now. So 2 has to be, it's the second position where we're putting the 1. 1 is where they agree. And 0 if it doesn't appear in T. So x1 doesn't appear, so we put a 0. x2 does. x3 does not again. x4 and x5 both do, so we have this for theta of T. And it's seen, as we mentioned earlier, that this is a bijection, and one can show that it's injective and surjective, but that'll just be omitted from this video because it's, I hope it should be apparent. Okay, now that we've gone through that problem, we would like to define the choice function. Sorry, I shouldn't use the word choice function because that is an entirely separate meaning in set theory with the axiom of choice, but we'd like to define this binomial coefficient n choose k, right? And you might have seen this, and you might have also seen an algebraic formula for this, but we want to derive that algebraic formula from a combinatorial interpretation of it. So first we let S be an n set, and we want to write this S choose k here as the set of all k subsets of S. So this is a set right now, but we want to define n choose k now, n being the cardinality of S, being the number of sets that have k elements. So we can think of n choose k as the number of k subsets in a set with n elements. We want to show this familiar formula here, that n choose k equals n times n times 1, so on, till n minus k plus 1 divided by k factorial. And you'll sometimes see that this is written as n factorial over k factorial times n minus k factorial, but this is equivalent since we've just cleared the n minus k factorial from the numerator. Here's a word about notation. It's a very convenient one because we have this really big long numerator. We sometimes write this as n with a subscript k, and this is written as n lower factorial k. So we want to show that n choose k is n lower factorial k divided by k factorial. And here we'll show the first example of defining that sort of tertiary or helping quantity to show that two things can be equal combinatorially to that, and then they have to be equal to one another by extension. So we define this quantity n of n and k, which is the number of ways to choose a k subset, T has k elements of S, and then we linearly order the elements. We'd like to note at first that the number of ways to choose this k subset and then the number of ways to linearly order it are independent. So whatever the numbers are for these two events, we can multiply them because they have no bearing on one another beyond the fact that we have now a k subset and now we can linearly order its elements. Okay, so we can choose T by definition right? We supposed over here the set of all k subsets of S. We can choose T in n choose k ways, right? So now we can use the fact that the cardinality of T is k, and we think about how many ways are there to permute or rearrange the elements of T. There are k ways to do the first one, because we can choose any of its elements first. Then we can choose k minus 1 for the second one, because we've already used one for the first. K minus 2 for the third, because we've used up the first two. So on and so forth, until we've filled up k minus 1 slots. And then the last one has to fall into place as the remaining one. And there's only one choice for that. And that is just k times k minus 1, etc. to 1. So we have k factorial, right? The number of permutations of k elements. So we've just found out now that n of nk is this n choose k times k factorial. And this is promising because actually now if we clear the denominator here, we have n choose k times k factorial. This is an interesting technique too, because looking at this kind of problem, it seems difficult at first. How are we going to interpret this k factorial in the denominator of the right-hand side? There's no clear way to do it. So if we clear the denominator and we define this new quantity, it might be easier to do so. Okay, so we've shown that n choose k equals this one thing. Now we want to show, it's enough to show that it's equal to this numerator here, because then we'll have shown this, this formula. So we want to show that it's equal to n times n minus 1 times n minus k plus 1. And again, this might ring some bells from what we actually just did with this k factorial, where we rearranged k elements. Except now this time, we start with ways to choose k elements from n. And now we have n times n minus 1, because we have n ways to choose the first. But we do have to stop at a certain point, and that's when k slots are filled up. And so for that one, we have n minus k plus 1, and there's k elements in this over here. So we have n equal to this over here, this term, and we have n equal to this different thing. Hence, they must be equal to one another. So n choose k times k factorial equals this n lower factorial k. And then dividing it by k factorial, we have gotten our desired result. Okay, so this is a very useful first thing to have, because permutations and combinations are both fundamental, as I said, to combinatorics. There is an alternative way of going about this, and looking at binomial coefficients through this method of generating functions. To do this, we want to regard x1 through xn as indeterminates, or variables, independent indeterminates, rather. We have 1 plus x1 times 1 plus x2, and we can take this product over these n variables. And this happens to be, you can work this out for small values of n just by multiplying them. It's equal to the sum, then for t being a subset, of the product of each xi being an element of t, xi being one of these. And so if we take each xi equal to x, right, we have this product over here, x here. And so this product is going to be taken as many times as there are elements xi and t. So we can raise x to the cardinality of t and clear this product. So we have 1 plus x to the n, because now we have x1 equals n, x2 equals n times. Sorry, x1 equals x, x2 equals x, n times. And that equals the sum of this product of x. And this equals, in turn, t being a subset of s, of x to the cardinality of t. And then converting this, by definition, we have for k being greater than or equal to 0, k denoting the cardinality of t, we have now n choose k times x to the k, because with this this exponent evaluated. Okay, so this is sort of a direct corollary of the binomial theorem, but it's also useful to phrase it this way. It's also an example of the slightly more general result. If we have S prime, let's say a collection of finite sets, such that S prime contains f of n sets with n elements. F is an unspecified function. We just know that it behaves in this way. That the sum over all sets S and S prime, x to the cardinality of S, is going to behave like this. And this is for the exact same reason now, and we'll see that this result here, binomial theorem being a directly follows from this, just taking f as the choosing function. More generally, and I'll state this without really going into it much because it's less important at this stage, if we have this function g from natural numbers to the complex numbers, also known as an arithmetic function, we have that this sum over here, s and s prime, g of the cardinality of s times x to the cardinality of s is going to be equal to this right-hand side over here. And I might go over this in something separate, but there's so much that one can do with these arithmetic functions. Okay, so this has been the first few results in enumerative combinatorics. I will see you in the next video, and thank you.